Excellent. Can everyone online hear me? Okay, so the game plan here is, let's see, some primer material. So game plan for today is to go through chapter 1 from the textbook, A Tour of Computer Systems. So the goal is after today, we would have covered the first chapter from the textbook. We have already lectured pretty in-depthly on the 2 primer PDFs that were part of the syllabus, the Central C and then the Unix toolbox. So if you had read the at least the older listing of the assignment that was listed on the 2467.cs.uno.edu webpage, you'll see that those are the 3 pieces of lecture material that kind of preface the very first assignment. So I'll talk to David about getting the first assignment actually published onto Autolab this week. So we should now all be prepared to be able to start working on it after today's lecture. Now, I will say that leading into the semester, I thought I was teaching a Monday, Wednesday class, and then very quickly, about a couple of days before the semester started, I got reassigned to a Tuesday, Thursday class. So with that said, I actually have a flight where I'll be on an airplane this Thursday coming up. So I'll likely won't have lecture, but what I'm probably going to do is reserve Thursday's traditional lecture time as effectively a self-study lab time. So I'm going to encourage all of you to kind of get onto the Discord, communicate with one another, and try to work out the very first lab assignment, asking for any help that you might have there. And as I get access to internet while I'm in and out of airports, I can go ahead and provide assistance as well. Okay, with that said, does anyone have any questions before we start with today's lecture? Excellent. Okay, so this should be a relatively brief lecture. I think the textbook, like many textbooks, start with a light side of the material, and then it's going to go into massive amounts of depth once we've kind of produced kind of a shallow overlay. So let's step through it. Chapter 1, A Tour of Computer Systems. And let me... Okay, so let's first provide a quick abstract as to what this chapter is about. This chapter introduces the major ideas and themes in computer systems by tracing the life cycle of a simple hello world program. So just like almost every other entry into anything related to computer science, it starts with hello world. Okay, so a quick listing of how this slide deck and how the actual chapter is broken down covers the content going from information and how it's defined as a collection of bits of context, all the way down to how programs are translated by other programs into different forms, then how it pays to understand why the compilation system actually works. Then we'll talk about how processors can read and interpret instructions stored in memory. We'll talk about why caches matter. We'll talk about how storage devices form a hierarchy and how operating systems manage the hardware. We'll talk about how systems communicate with other systems using network. We'll very quickly run through the important themes. And really, I think out of that section, there only the latter one is the one that I was really concerned about. And finally, the summary slides are provided, but we won't really go through those in depth because we would have covered everything previously. Okay, so quick preface before we actually start on the first section. Let's talk about how we're going to define a system. So we're in system programming concepts, right? So what is a system? And in specifically, I mean a computer system, because our book is called what? Computer Systems, a Programmer's Perspective, right? So CS in that instance. And sometimes we'll just refer to it as a system. So we can think of a system consisting of both hardware and software that work together to run application programs, right? So when we walk through today's kind of hello world program, we're going to look at it from the perspective of the software side, and then we're going to unpack that and look at it from the hardware side. And so this, again, learning about systems in the vein of how we can use system level software and then have considerations about the hardware is really going to bring us to the level where you're going to need for when you go into OS, into operating systems. So that means our learning objectives here over the course of not just this slide deck, but by the time we're done this textbook, is that you're going to learn some practical skills, such as how to avoid strange numerical errors caused by just the way that our computers represent data, especially numerical data. We'll learn how to optimize our C code using various clever tricks, because we'll look at how the computer organizes and manipulates data, and we can take advantage of those rules once we understand what those rules are to maximize performance. We'll learn how the compiler implements procedure calls and how to use this knowledge to avoid security holes. We'll learn how to recognize and avoid nasty errors during the linking that can sometimes confound the average programmer. We'll learn how to write our own Unix shell. That's going to be one of the labs. I want to say that's traditionally lab 5. And we'll learn the promises and pitfalls of concurrency, which is a really important skill set, more so now than ever before with the emergence of these very large language models and these new data science techniques that are out. Okay. So this chapter in particular is going to be the tour of the computer system. So again, we'll use hello as just a very simple program, but every part of our computer system has to work in order to do something as simple as running an application and displaying text to the screen. So the goal of this course will be to help you understand what happens when and why we run the hello in our system. And again, hopefully to build a really deep foundational knowledge on that. So a quick overview from the software perspective. So we're going to look at the hello program. Software side, we're going to begin our study of systems by tracing the lifetime of the program from the time it's created by a programmer to when it's compiled into an executable, to when it launches on the system, to when it prints its simple message, and then finally exits and terminates, right? That's the life cycle that we can probably state up to this time when we go to run any application or author and then run an application. Okay, so let's look at our software. This is going to be the actual source code we will look at. And again, you're going to do something very similar to what's happening in the slide deck in the very first assignment. So here we have that hashtag include standard input, right? So that's some library functions. We are going to create a function, right? Main, that's going to return back an int type, and we're going to go ahead and give it a code block. Inside the code block, we're going to make use of that system input output function to use printf, and we're going to pass printf a string literal of hello world, and then a new line character, right? Very simple program, not dissimilar to Java, pretty much what we've seen in Essential C from the earlier lectures we've seen. Okay, so let's see what happens to actually get this to execute. So again, stage 1, which has nothing to do, well, a little bit to do with the system, we have to first create that source code file inside of an editor. Now, we had mentioned last lecture, you can use system level text editors, but that's not necessary. There's lots of GUI based text editors. There's really rich text editors. You could author this file in any one of those, right? The important thing is that when you're done, you have named it hello.c. .c is the extension we're going to use for our C source code files. So the source code file is simply just a sequence of bits. We talked about that earlier too. Where a bit is just a binary unit, which means it can only have 1 of 2 values, a 0 or 1. And so for our characters, for our source code file, in this instance, it's encoded in bytes, which is an 8-bit chunk. And so each byte can represent a character in our program. So computers represent text characters using the ASCII standard. And because it only has 128 representations, unique representations, it's good for the Latin encoding, but sometimes you need to have UTF if you want to have a larger character set. Okay. And of course, we can represent our these as integer values, right? That's effectively what we're encoding, but then we have a visual representation based off of the glyph for our own purposes. So if we were to go ahead and retranslate what we had in terms of our source code and see how is it actually now being numerically encoded based off of the ASCII text representation, we could see we could do a one-to-one correspondence here. So for each character, we can underneath it produce a numerical value, which then gets encoded into our file. Now, if our file is designed to use these ASCII characters, we would call that a text file. The nice thing about text files is that they're human readable, right? When you open them up in an application that understands it's a text file, it'll retranslate it into your characters so that you can go ahead and read it. All other files that are not ASCII encoded, that are not ASCII characters, we would refer to as binary files. And then you'd have to have whatever the context is for that binary file to be able to be decoded into something useful. So say, for instance, a JPEG, for instance, is just another type of file. But if you have an application that knows how to encode and decode JPEGs, you can go ahead and open it up and view an image. Same thing with an MP3, right? An MP3 file is just another binary file. You use a special application that knows how to decode, encode MP3 encodings, and then you can go ahead and listen to music. Okay, so this brings us to the very first subsection of this chapter. Information is bits plus context. So all information in our computer system is encoded in bits. That includes our disk files, our programs that are stored in memory, our user data, the data that's transferred from our application to some other networked application, right? It all happens in bits. So considering everything's encoded using the same concept, it's the fact that we can provide context on top of that bit sequence, in which case it becomes meaningful, right? So we can use the same bit representation, but if we give it the context that it's supposed to be an integer or floating point number or a character string, then it translates into different results. Okay, let's move on to the next section. We talked a lot about that, I think, in the last, so still kind of building up to this notion of how is this going to translate into hello world. Okay, so we now at least talked about how we could create a source code file and then how that source code file can be represented and encoded into our computer system using bits. Now let's talk about, okay, once we have our source code file, how does it then become something that can run on our system? How does it become actual software? How does it become an application? Well, that has to go through a compilation system. So the hello program begins as a high-level C program, and we call anything that is human readable in the form that we can parse it and understand it as something that's high level, right? It has abstractions there for us. Now, when we go to run this, we're going to have to translate that human readable text into some low-level machine language instructions. That process is our compilation process, but it actually has 4 different stages it's going to go through that we're going to see. From the general perspective, when we create our C code and when we compile our C code, and this is not dissimilar from any other compiled language, whether that's like, for instance, Java, where you can go ahead and from your system invoke the compiler to give it your source code and then convert into, in the case of Java, it's bytecode. In the case of C, it's going to be our object file, our object code. So here, the one-stop solution would be we would invoke GCC, which we learned about already. We would go ahead and tell it what source code file we want. So that's the hello.c you see in here. We can give the outputting file its own label identifier. So the -O and then hello is a flag to say, hey, compiler, don't default to give it a default name. If we don't do the -O, if we could just call the compiler and give it a source code file, and then it'll give a default label like something like a.out or something, right? But we can also enforce a naming structure on what our executable is going to be. So right here, the result is this is going to create an executable object file for us. Now, it gets we can open up that box. We can open up this compilation system box and peer into it and see it gets a little bit more complicated than that, right? And in fact, the compilation system is actually a collection of multiple programs, and each of these programs you have access to from your shell, and they're each independently accessible. In fact, what you see at each one of these little boxes inside of this kind of flow chart you're seeing, under the preprocessor, you'll see it's CPP. Under compiler, you see it's CCL. You see after assembler, you see AS. After linker, you see it's LD. Those would be the command lines you would use to invoke that portion of the application. And again, that's something you'll actually see in the very first lab assignment. So what we're going to do is we're going to very quickly go through each one of these steps here of the compilation. So we start with a hello C. That's our source program file, which is a text file, right? Notice we're going to put that through our preprocessor, and it's going to change the extension. We'll talk about more of this in later in the next slide, but the result is going to be another text file, something that's still ASCII encoded. Then that passes to the compiler. That's going to end in an extension of .s. At that point, it's going to be an assembly program. That's going to go through an assembler, where that's going to become an object file, right? And so then that object file might have to get linked with other object files to produce your executable. So very quick definition of what happens to get your complete executable file, but let's actually talk a little bit more. So our pre-processing phase here. So it modifies the original C program according to the directives. Remember, our directives are the things that we preface with a prefix with a hashtag. So it looks for that hashtag symbol, and it'll go ahead and be able to insert into your source code file the instructions, the things that are labeled inside of your preprocessors directives. And so in these instances, is going to produce your new file, which would have the .i extension, which if you used the GCC, this would naturally funnel from one to the other to the other. Okay, so let's go to the compilation phase. The compilation phase then takes what had come out of our pre-processing step, and it's actually then going to take our text file and convert it into our assembly language program. And so here's an example you can see in the slide of how we then would translate our hello world program in C and actually see the assembly instructions that it would then get encoded into. Okay, so once we go from the assembly phase, and the term that we would use for this at this point would be called a relocatable object program. Once we get through this phase, it's no longer human readable. If we were to open this into a text file, it would just look like garbage, right? Like it would try to decode it into just random characters. And then the last phase, once we have the object file, well, since we're using calls outside of just our own application, right? We were importing standard IO so that we can access the printf function. Well, that printf function has its own object file that's separate from our object file that represents our hello world program. So the linker has to take all these relocatable object programs and link them together so that they can be used and build from that an executable object file. And the executable object file is then what we can invoke from our shell and actually execute. Okay, so at this point, we've now talked about how we can go from our text editor and how our text editor actually represents the characters in terms of data inside of our system, and then how we can take that system and use other applications to translate into something that can then start executing. Let's talk about why it might pay to understand how your compilation system works. Like what, since this is so automated, since I can do one line of code, why is it worth your time to spend an entire semester really cracking this box open? And really, the big three reasons that one can argue is you can learn how to further optimize if you know how the underlying mechanics work. So, say for instance, you'll know nuanced details. So you can ask yourself, in what way should I index into complex data structures that are multidimensional? Does going from left to right to left indexing make a meaningful difference? What happens? What's the cost of making a function call? Lots of interesting nuanced things we can start to investigate that you'll get a greater understanding for as we continually kind of get closer and closer towards how our system is going to go ahead and break our source code down and actually execute it. We'll get a better understanding of link time errors. That's one of the more complex issues on why when you get a bug, you might look at it and it might not be meaningful, because that's where a lot of the magic happens. And then, and by magic, I mean a lot of the automated building that we're not normally concerned about. And then finally, it's going to behoove you, because it'll allow you to understand how to avoid security holes that you would not be aware of without having these deeper understandings. Okay, let's move on. So processors read and interpret instructions stored in memory, right? So let's go back to our run the hello program. So to run the executable file on a Unix system, we would type the following into our shell. So here, imagine if this is just the prompt that our shell gives us to us to say, hey, I'm awaiting some command. If we want to execute, now that we've compiled our application from source code into an executable object file, we can now use our shell to execute it. So if I do // and then the name of my executable object file, it's going to go ahead and run that. And you'll see the output that's then set to my shell would be hello world. And then after it displays hello world, it'll then go ahead and show a new kind of prompt to illustrate, okay, what's your next command? I'm open and available, I'm not processing anything at the moment. So let's start with the shell. The shell is our command line interpreter that prints a prompt, waits for you to type a command line, and then performs that command. If the first word of the command line does not correspond to a built-in shell command, so for instance, there's lots of shell commands you probably already know that it'll see if it's inside of its built-in dictionary, its collection of directives and respond. So like, for instance, ls is one that's built into our shell that will give you data regarding your file system, right? Like it'll list whatever the current contents are depending on what other modifiers you put afterwards. Now, if there's no kind of reserved command that you have put in, it's going to assume that you're trying to run some external executable object file. And that's why sometimes if you mistype something, it'll say it can't find that particular resource. Okay. So let's see here. If the first word of the command does not correspond with built-in shell, then the shell assumes that it's the name. Yep. And in the above case, the shell, and we already talked about this, it loads and runs our hello program. The hello program prints its message to the screen and then terminates. The shell then prints a prompt and waits for the next command. Okay, so let's step back one layer deeper now. So we know how, or we mentioned briefly how the shell works. Let's talk about the hardware perspective, because on the very first slide in this section, we said that a system is a combination of software and hardware that has to work in together to go ahead and run our applications. So from a hardware perspective, to fully understand what's happening in our hello program, we need to examine the organization of our computer system. And then we'll look at how that works together to kind of flow the hello program throughout it. So important critical hardware components are going to be buses, I/O devices, main memory, and our processor. And again, I'm assuming, I'm pretty sure these hardware level components are at least mentioned inside of assembly as well. And if not, you'll definitely go deep into them with computer organization, which is, I want to say, is 3301. Okay, and here I just have a quick kind of depiction of how we might want to consider our hardware organization inside this illustration, which is pulled from the textbook. Okay, let's talk about buses. So our buses run throughout the system. They're a collection of electrical conduits, and their purpose is to carry bytes of information back and forth between components. So hence the term bus, right? Like you're busing things around your system. Buses transfer a fixed number of chunks or a fixed size of chunks of bytes known as words. And words can either be 4 bytes or 8 bytes, depending on the architecture of your system. Our I/O devices are the system's connection to the external world. The purpose of each is to transfer information back and forth between the I/O bus and the I/O device. So again, if we look at our illustration here, we have our I/O bus, and from the I/O bus are all these devices that would be connected to it. And then the only way into the actual CPU, we'll get to the idea behind the CPU, although I have a feeling you already know what the CPU is used for, is through these buses. So our I/O bus would include things like our keyboard, our mouse, and that would be for input, our display for output, it would be our disk drive for storage, right? Everything effectively is attached to the I/O through our I/O devices, or our I/O, everything would be an I/O device, and it would attach effectively to the I/O bus that we kind of think of meaningfully of how we get data in and out of our applications while they're actually executing. Okay, let's talk about main memory. The main memory is a temporary storage device that holds both a program and the data it manipulates while it's executing. You could think of our main memory as existing as something that is both a physical entity and, almost more importantly, a logical entity. Physically, it is our RAM chips, right? More importantly, you want to think of it as an organized linear array of bytes, each with its own unique address. And our starting at 0, if you want to think about addressable space, right? So a unsigned value. And now finally, we have our processor. So the processor is effectively the engine that interprets or executes our instructions stored in main memory. The CPU is a word-sized storage device, right? So it does have registers that hold very small, I can't say bits because that actually means something. So very small units of data. And it also has our program counter. Again, you learned how to manipulate both the registers and the program counter, as well as probably your the available stack in assembly. So a processor executes your instruction pointed at by the program counter, and then updates the program counter to point to the next instruction. A processor appears to operate according to a very simple instruction execution model that we will call the instruction set architecture. So let's define that instruction set architecture. Instructions execute in sequence in a series of steps. They are: the CPU reads the instruction from memory pointed at by the program counter. The CPU interprets the bits in the instruction. The CPU performs some operation defined by the instruction, and finally the CPU updates the PC or our program counter to point to the next instruction. So our operations that these instructions set architecture would interface with, what it communicates, what it can modify, what it can control, are going to be either the main memory, the register file, or the ALU, our arithmetic logic unit, which is all what you see kind of housed inside of our CPU inside this diagram. Okay, and then there's a couple of simple functions that are part of this instruction set architecture: the ability to load bytes or data in, the ability to store, the ability to operate, and the ability to jump, right? And again, you've done this in practice, so you can see how, based off of these very basic set of instructions, it allows us to create logic that can branch, logic that can repeat, logic where we can store, mutate, get in data, get out data, effectively build any software we want. It just happens at a very low level. Okay, after very briefly running through the primary components on the hardware side, let's now look back and see the flow of our application through the hardware. So the first thing that has to happen is the shell program is waiting for us to type a command. We type the characters that execute our application. So in this case, it would be ./hello on the keyboard. So here, at this point, we would be through here, our USB controller, because we're doing that from the keyboard. So the flow into our hardware is going to start from here, and then it's going to hit our I/O bus. So then the shell program reads each into a register and stores it in memory. So it goes from here into the I/O bridge, into the memory interface to get to this register file that then can be executed by our CPU. So we're not there yet, though. The shell then loads the executable. Okay, so the shell program reads into register and stores it in memory. The shell then loads the executable hello file by executing a sequence of instructions. Now we're executing on the CPU. And what we'll then do is we will copy the code of our hello object file from the disk drive into memory. So the first thing is we have to transfer it from disk into memory so we can actually start executing it. Okay, so notice I tried to line these up so you can actually see an animated view as I step through these slides. So then the next thing is the data travels directly from the disk to the main memory without passing through the processor. So that was this transfer from our disk. We go through the disk controller because, again, everything goes through this I/O bus, go to the I/O bridge. And at this point, we don't need to be processed yet. We need to be loaded to memory before we start executing. So then we go right into memory. Then the processor begins executing the machine level language instructions in the hello program's main route. And so then once we have access to things in memory, we can then go through here and then go through our I/O bridge, go back to our I/O bus, and then display our graphics adapter. Through our graphics adapter, we can then display hello world, which would then appear on our shell. Excellent. Okay, so that's just a very brief kind of abstract view of what's happening at a hardware level when we run our hello world program. Okay, let's move on to the next concept, because you probably saw just in that very brief example that the system spends a lot of time moving information back and forth. When we talk about optimizing, when we're talking about how can we get our application to run quickly, right? These are going to be considerations. How often are we writing and reading? And from where are we writing and reading? Because that's going to have significant impact on how your applications run. Okay, so in our hello world program, the machine instructions in the hello program are originally stored on disk. And when the program is loaded, they're copied to the main memory. And then as the processor runs the program, the instructions are copied from main memory into the processor. And then from the processor, then they're delivered back to they're then displayed out into your monitor. So you can see there's a lot of transactions happening just to run that simple application. And so these are where we start having to think about speed size trade-offs. So think about it this way. The disk drive on a system may be 1,000 times larger than your main memory, than the amount of RAM you have. But it might take your processor 10 million times longer to read a word from your disk than from your memory. So you get larger volumes of data, but it's at much slower access, availability. Whereas your register file may only store a few hundred bytes of information, as opposed to the billions of bytes that are in your main memory. Again, when your application's running, it has to be either in memory or it can be in your register space. However, the processor can read data from the register file about 100 times faster than it can from your main memory. Again, considerations to think about. Now, this does lead us to looking at cache memories. So to deal with this processor memory gap, the systems include smaller, faster storage devices that are called cache memories that serve as temporary staging areas for information that the processor might likely need. And you have different levels of this cache memory. L1, L2, L3. We'll actually look at a hierarchy of that. The idea behind caching is that a system can get the effect of both a very large memory, being able to store lots of things, but also things that are very fast. Because ideally we want both, but we can't have both from the same type of data. It's just physically impossible. You can't maximize speed and size simultaneously. But one thing we can exploit to try to increase the amount of size we have and still keep very fast is this idea of locality, where there's a tendency for our program to access data and code in very localized regions so that we don't have to constantly search the entire space of our disk or whatever our memory space is if we're running a particular application. Okay, which allows us to start developing this pyramid, this memory hierarchy. So the idea of a memory hierarchy is that our storage at one level serves as a cache for the storage at the next lower level. So the fastest is at our pinnacle, it's at the top of the pyramid, and as you flow down, it gets slower and slower, but it gets larger and larger. So for instance, our register file is a cache for the L1, will cache for our L1 level. Our L1 level can cache for our L2 memory, our L2 can cache for our L3, the L3 will cache for the main memory will then cache for our disk drive. And here you can kind of see how this flows out. Okay. Let's step back. We talked a little bit in terms of the applications, we talked a little bit about the data representation of how our Hello program works. We talked about what applications, what programs we need to translate our source code file into a executable object file. We talked about programs such as the shell that we can then use to cause our application to then execute on our system. We looked very briefly at the components that make up our hardware system and how our program, our Hello program, flows through those hardware components. Let's now look at the middle ground step between the applications that we use to author, to compile, and then even to invoke or call our object file, our executable file, and that actually then interfaces with the hardware components. That's going to be the operating system. So it's the operating system that manages our hardware. So programs, all programs are going to rely on services provided by the operating system. The operating system is a layer of software that's interposed between our application layer and the actual hardware. All attempts by any application to manipulate the hardware have to go through the OS. And so if we want a visual of this, the LAN we have existed in previously is here. This is our application programs. And on top of, sitting underneath us directly is the operating system. So these two layers build out our software, and then the operating system itself is on top of that hardware architecture that we had talked about previously with our IO devices, our main memory, and our processor. Okay, so what is the purpose of looking at the operating system? Well, it serves two primary purposes for us. First is to protect the hardware from misuse by runaway applications, right? It provides a defense. And second of all, it provides applications with a nice, simple, and uniform mechanism for easily running, interfacing with things like network driver. It uses network drivers to be able to send data or to access your display, or to be able to send out audio, or to capture data from keyboards or from mice, right? So instead of having to know inside of your application how all the hardware particulars work, right? That's a really complex task. You can ignore that. That can be abstracted away because the OS will worry about how all the hardware that's attached to the machine actually captures that data, and then it creates a mechanism where it can just send that data to your application. So there's an advantage on both ways, right? It helps protect the hardware, and at the same time, it produces a nice, uniform, easy interface so that you can just worry about creating applications that run at the OS level. Sorry. Okay. Let's see. Now, the OS achieves these goals via abstractions, right? So we've learned already the power of abstractions at a high level language. But it's not just at a high level where abstractions are meaningful to us. It's not just defining things like classes and instances when we're building our applications. In terms of our OS, the abstractions we care about are processes, which is an abstraction for our processor, our main memory, and our I/O devices. Virtual memory is a abstraction at the OS level that allows us to abstract the main memory and our disk I/O devices. And then finally, files are an abstraction of I/O devices. So if we were to look at this as a hierarchy, anything that's effectively a sequence that we might get from or send to an I/O device, we can represent as a file. Anything that we might need to represent in terms of main memory or as I/O devices could be captured with this concept of a virtual memory. Or when we start talking about having access to the ability to process, store, and capture input and output, we can think of that more abstractly as a process in and of itself. So you can see how you can go all the way up in terms of these terms. And we just define this. A process is the operating system's abstraction for a running program. So multiple processes can run concurrently on the same system, and each process appears to have exclusive use of the hardware, but that's not true, right? By concurrently, we mean that the instruction of one process are interleaved with the instructions of another process. So in most systems, there are more processes that are running on your system than you have CPUs to run them. So how does that work? So there's this concept of context switching. A quick explanation of what context switching is. The operating system keeps track of all the state information that the process needs in order to run. And again, we can think of a process as something that is doing some kind of taking availability from the processor, main memory, and I/O. So in this instance, and we'll look at an example, we're going to bring this back down in just a moment to our hello program. Okay, so but let me go back here. So in terms of context switching, the operating system keeps track of all the state information that a process needs in order to run. And the state is also called a context, which includes information like the current values of our program counter, the register file, the contents of main memory, right? Everything that the application needs to be able to do the next stage of what it needs to do before it terminates. So at a point in time, a processor can only execute the code for a single process. So given that constraint, when the OS transfers control from the current process to a new process, it performs a context switch by saving the context of the current process and passing that control to the new process. So let's look at this now. After explaining it, let's look at what that means in terms of our hello program. So there are two concurrent processes in our example scenario, right? You have the shell process that we had to open and interface with, we had to communicate, we had to send commands to launch our application, our executable object file, our hello world application. Then we had another process that represents our hello world process actually execute. So when we start, let's step through how this context switch works then. So here, going downward represents time. And then you'll see we have two columns, one that represents when our shell process is executing, the other column represents when our hello process is running. So we start in our shell process, and the shell is running alone, just waiting for input on the command line. So when we ask it to run that hello program, the shell carries out our request by invoking a special function known as a system call that passes control to the operating system. The operating system then saves the shell's context, creates a new hello process and its context, and then passes control to the new hello process. So this transfer between these two processes is then happening at the OS level with a context switch. Now, inside this process, and you can see we have our context, this is the OS, so we're running application code, then we're running OS code. Now we can run our application code. This is our hello process. Inside of here, we will do what we were doing inside our hello world program. So effectively, we're going to do what we mentioned before, right? We're going to load all of our data into memory. We'll go ahead and then execute it through our CPU, and then route our string hello world to our display device, right? And then send that out. And when that's done, that's all that's in our main function. So then we'll return control back to the OS. Once we return control back to the OS, it's going to do a context switch again, and then switch back to our shell application, our shell program, which will then sit and wait for us to go ahead and issue another command. So the transition from one process to another is managed by the operating system kernel. So if you've ever heard of the kernel of the operating system, that's one of the roles it has. The kernel of an operating system resides in memory. It's always running in memory. It's a collection of code and data structures that the system uses to manage all of our processes. Okay, let's talk just briefly about threads. In modern computer systems, a process can actually consist of multiple execution units. So these multiple execution units can be called threads. So you can have one process that can spawn multiple threads, each running in the context of the process and sharing the same code and global data, right? So one process can compose multiple threads, but they're all part of the same process. Okay, virtual memory. This is the other abstraction that we were talking about. Virtual memory is an abstraction that provides each process the illusion that it has exclusive use of the main memory. Each process has the same uniform view of memory, which is known as our virtual address space. The topmost region of our address space is reserved for the code and data that the operating system is going to use, that's common to all processes. And the lower region of our address space is going to hold the code and data defined for that user's process. And then addresses in this figure are increasing from bottom to top. So let's talk a little bit about the regions. The virtual address space seen by each process consists of a number of well-defined regions. We could say it has a program code and data region, our heap, our runtime heap region that would be available to us, shared libraries region, the stack region, and our kernel virtual memory region. That's what you see all defined inside like this segmentation. Okay, then we had that last abstraction we were referencing, files. So a file is simply a sequence of bytes. It's nothing more than that, right? So everything in our OS is effectively represented as a file. Even your folders are effectively just a special type of file. Every I/O device, including disks, keyboards, displays, and even networks, is modeled as a file. All input and output in the system is performed by reading and writing files using a small set of the Unix I/O or whatever your OS I/O would be. In this instance, we're going to be using Unix inside of this course. And of course, the motivation behind using this abstraction of files is that it's a simple and elegant notion that allows for applications to have a uniform view of data, of how data streams work regardless of what that IO device is, whether it's memory, whether it's a disk drive, whether it's a keyboard, whether it's a mouse, whether it's a network adapter, whether it's a monitor, right? The concept of how data flows is uniformly the same. That proves to be a very powerful concept. Okay. Let's talk a little bit about networking, and we're going to bring this back to our example, a Hello World program as well. So systems communicate with other systems using networks. And especially in today's day and age, right, more applications probably network than not. So systems are typically linked to other systems by networks, and the system considers the network as just another type of IO device. So here you could see if we update our figure, you could see connected to our IO bus is all of a sudden a network adapter. Connected to the network adapter is going to be a network. You'll see that you actually, let me make a brief mention about this. This was defined inside the textbook, and I see it's inside the figures here. So I'll just articulate. If you see something called a controller versus an adapter, those typically mean the same type of thing. It's a type of IO device. It's just how does it interface into your motherboard? A controller is typically hardware. It's a chip that's embedded into the system itself, whereas an adapter is something that can plug in on top of the machine, right? You can adapt into it and provide new functionality. The end result's the same, whether you install and whether you have an Ethernet port hard coded like soldered to your motherboard, or if you get an Ethernet port by installing it into like a PCI slot, right? The end result's the same. But if you just want to know what the difference between controller and adapter, that's just what it's articulating. So suppose I have a network adapter, which now means that's the card that's installed in our system. Then I can attach a network to that, and the data that flows in and out of that network is now just thought of as any other type of IO device. So networks are nothing really special, right? At least from the perspective of how we can think of data flowing in and out of our application. So if we want to see how we can bring this back to our Hello program, we could think of using, the book uses Telnet, but we could think of using SSH as a comparable replacement for Telnet here, which is going to be something that I think you might be using. I don't know if we have access to SSH on the networks anymore. Oh, Telnet. Well, either way, this example still works. So in this example, you'd have, say, for instance, your user who types hello at the keyboard, and the client then sends that hello string to the Telnet server. The Telnet server sends the hello string to the shell, which runs the hello program and sends the output to the Telnet server. The Telnet server sends the string to the client, which then displays it. So you can see how we can effectively take this data capture, and it's no different than if I were to take it from the keyboard and send it to a local application versus a networked application. There's nothing fundamentally different. Okay, the latter part of the first chapter then talks about some important themes. The three important themes that are stated in the book are Amdahl's law, concurrency, and parallelism, and the importance of abstraction in computer systems. The first two we'll just ignore for now, because those aren't going to be as critical for our Hello program tour of a computer system. These are additional things that might crop up like weeds as we cover the concepts. So as we encounter them, we'll talk more deeply about them. But the latter one, the importance of abstraction in computer system, I think is worth spending just a little bit of time to talk about. So here we can say that the use of abstraction is one of the most important concepts of computer science. Probably from the day you started to code, you were learning about methods of starting to abstract. From the very first moments of even probably right after you did Hello World, you're probably told in lab instruction or whatnot how you can start improving it and abstracting it into something better, right? And as we showed earlier at the OS level, when we were talking about abstractions, about virtual memory with files and our processes, that's going to be true at every level of computer science. So for instance, at the software development level, and this isn't just true with high-level software, it's true with low-level softwares too, the concept of APIs is something that's very powerful, these application programming interfaces, which can have a set of functions that allow programmers to use code without having to delve into inner workings. Anything that has a standard library effectively has an API. And in fact, APIs exist in assembly, that's like your instruction set. They exist in C, that's the standard library. In Java, that's your standard library, right? If you build code out, and if you use Java docs to expose publicly available methods and classes, you were building out an API. Okay, so we could say our abstraction mechanism that we've kind of motivated up to this point is inside of this illustration. We looked at this. This is a more complete version. We'll talk a little bit more about that in the next slide or so, where with our I/O devices, we can just subtract any of those into just the files. And then if we also need memory attached to that and not just byte sequences, then we can abstract that into virtual memory. And then if we need processing units on top of that, we can abstract a combination of all three of those into processes. And so this processor itself has an abstraction, which is our instruction set architecture. And then finally, if we need to abstract even with that operating system, we can do virtual machines. And we'll see, we already talked about the processor abstraction, which includes this instruction set architecture. We already talked about this OS abstraction that talks about files and virtual memory and processes. Of course, there is one new abstraction that we see in this slide that wasn't mentioned in the prior slide, which is the virtual machine, which provides an abstraction of the entire computer, which is, again, become very, very popular. In fact, if you go into the domain of DevOps, they are in a position where they are in support of developers, where they go ahead and can build out environments that are pre-configured with all of the software tools, with all the versions of the OS and everything else you need as a developer to start working, so that you don't have to spend your time configuring your environment system. So that is a huge domain in CS right now, and that's empowered by this concept of starting to even abstract away things like our OS and our runtime environments. And if you've ever used Docker, that's one of the big things that Docker provides to you. Excellent. And then finally, we get to the end of the chapter, which is our summary section. So that is our first chapter. We were able to actually get through it much quicker than the primer materials, I think. But I think that the book did a really good job of breaking it down. Does anyone have any questions about any of these concepts? Has everyone read these chapters already, out of curiosity? Did you find that the slide deck helped with the comprehension of the chapter if you already read it? Excellent. Well, we completed our slide deck a little, I think, sooner than what we had classes for. And yeah, it's going to work like that sometimes. So some chapters will be quicker than others. So if we don't have any questions, I'm gonna make sure, gonna ask online people. Excellent. So if we don't have any questions, I don't see any reason to hold people up for an additional 15 minutes. I'll just say that this represents now where we need to be to actually start working on the first assignment, because now we've taken a delve at looking at C syntax, and we've looked at the tools that are available at the system level from our shell. And now we've looked and inspected about what the tour is and what you're going to see if you've read through the lab. And again, let me highlight this. Let me go here where you can kind of pre-read where you get this. It's going to be 2467.cs.uno.edu. If you go here, and I think I have this posted on our Discord as well, right? Everyone join the Discord if you haven't already. And I've assigned roles, so I'll make announcements doing at 2467 to students that way. So That'll be like the mandatory learning management system we'll use. But if you want to kind of inspect the assignment, you could see it right here. And you'll see that the assignment has right here, it uses those two PDF documents, the Essential C and Unix programming tools, and it does chapter 1. So we are good to go. And if you actually look through this, actually, since I have some spare time, I can actually kind of briefly give you expectations of what you want from this. Probably good use of my time, so that you don't have to read it in solo. So here we can see inside the introduction that we now hit all the prereqs, introducing the tools. We've already talked about the tools. What do you have to do? Okay, so this section here will show you that you can access a pre-configured system either through systemslabweb.cs.uno.edu. You could also use the web terminal to be able to access the system through the browser at least. So Guacamole is one way you can access this. You can also access all of your environment stuff, your OS, your course material through these thin clients as well, both on the second floor. That's in what 209, in 212, or in any of these labs that have thin clients. Okay, all of what you're going to have to turn in, and the turn-ins are happen through Autolab, not through GitHub or GitLab. So everything will be provided to you. Once I get talked to David, there'll be a tar file, so that your handout will be available on the Autolab, where you'll be able to download it and you'll be able to untar it. Tar files are effectively like compressed files. So the lab document actually shows you how you can uncompress the provided documents so that you can edit them and then submit them. And I think when you go to submit them, you'll go ahead and recompress them for submission. And again, just follow the submission guidelines on the lab document. But the lab is broken down to 3 different parts. The first part just has you filling in a little bit of C code, building a prototype, making a application, making it so that you can actually run your application. You just go ahead, and I would again advocate follow along. If you have any problems understanding what it's asking, you can go ahead and send me a message. But the first part is with C. There is a extra credit component if you do decide to make a make file to be able to build it out. Yeah, here we can see this is going to be examples of the prototype that you might go ahead and define for your structure. Then the second part is going to go through the life cycle of the C program. This is what we just talked about today, right? And so for this, we're going to take that hello program that we actually discussed, and you're actually going to utilize each of the 4 stages of the compilation system and make annotations, say for instance, to your hello.i, look at it after just running the preprocessor on it. You'll be able to go ahead and kind of inspect what happens after you go through the compiler. But effectively, it shows you inside of this lab how you can go ahead and access and inspect elements from each of the various stages as you go through and kind of hand compile everything. And then finally, on the third part, you're going to look at performance differences. Okay, let's see. Let's go down here. Yeah, here. The third part is going to be to evaluate performance differences of just copying elements of an array based off of, we were talking about this before, about why it's meaningful to understand what's happening at the lower levels of the system in terms of compiling and executing your code using from left to right indexing versus right to left. Is there a performance difference? Well, that's going to be an answer you're actually going to be able to provide after this lab. In fact, you'll be graded on providing it. And then that would be the third and final part. And then here you finally have a wrap up section where you can then go ahead and it will explain to you how to actually do your submission and what all the names of your file should be. And again, with AutoLab, everything has to be very precisely named.
Exactly.
Yeah. So excellent. So this is the lab. You can kind of pre-read it now. I'll talk to David about getting the content, if it's not already available for you to start submitting on, to get it submitted. But does anyone have any questions about this?
So I know I was just wondering when this one's due for us. I'm guessing the due date.
No, yeah. So I think what would be a good due date for this particular one? It's a relatively easy one. We've spent a long time kind of like laying the framework down for this. So I'm thinking likely a week, giving a full week on this. And so let's see, we do Tuesdays and Thursdays. We're not meeting for next Thursday, but what I'll do is I'll make the due date the Thursday after. So we have this Thursday, and what I want everyone to do is, in lieu of having lecture this next Thursday, it would be great if we can meet through Discord in some kind of way. Again, I'll be on a flight, so I don't know how available my internet would be, but I would love for the class to be able to kind of collaborate with Q&A and be able to provide so insight as they go through this process themselves, so that you and then also this space will be open. So for those who are face to face, I encourage you to come in and then work in person, right?
And next Thursday, when you're going to be out of town, maybe first Thursday.
So it's going to be this Thursday. I'm going to be out of town so in 2 days I'll be on an air flight. So we won't have class this Thursday. So I'll encourage everyone to start working on the lab and so instead of thinking of it as we don't have class, think of it as a lab class. And I'm going to encourage all of you, both online and in person, to work together on this assignment. Now, in this assignment, it says it's an individual assignment. I don't care if you help each other. I just don't want one person to not do any of the work, right? That's where it crosses the line. But I think that there's a lot to be learned with people helping other people. Excellent. Is there any other questions? I have a question. When are we covering content for chapter 2? Chapter 2 will get covered next lecture. So we're going to roll. We are done with chapter 1, which means I'm going to start lecturing on the next chapter next. And I'm going to go sequentially. So do we have SSH access or not? I don't think so. So they have really tightened what we can and can't access through our network.
And we can't even.
Yeah, the computer science department doesn't have control over this. So where we had control over our network up until last semester, when there was 5 different higher education institutions that got compromised in a massive attack, they hardened with draconian restrictions our networks. But what you can do is you can go and use Web Terminal, or if you look, there's a hyperlink in here at the very top, which goes to Systems Labs. You can use a web portal that will use Guacamole that allow you to access a OS that you can then access your workspace from. So you can, that's not SSH, but it still allows you to remotely access everything that way. And I think I showed that, right? One way, let me show you, since we have the time, I'm going to jump to it. If I were to go to my computer science UNO page here, if I go to student resources, and I can go down here, there's lots of useful applications that you might want to know about. One of these is the CSCI web terminal. And if you click on this, it should go ahead and allow you to actually access right from your browser the Systems Lab OS. Yeah, see right there. Click on that and it'll connect using Guacamole. Then I can use my login credentials. And this is exactly what login looks like, right, on the thin clients, right? So this, effectively, I'm using the browser like a thin client. See if I can remember my password. Yeah, see, perfect. And if I wanted to, I can launch a terminal, right? And then I can create files if I wanted to from the terminal, or it even gives me the same kind of GUI interface that I'd have from the same client. So if you can't SSH in, you can still do this. Does that answer your question? The chapter, so questions about where the availability for the slides. I don't like Canvas anymore, so I'm using Discord. Go to Discord. Let me see if I have Discord on this machine. Let me show everyone and make sure everyone, since I have the availability first, let me kill process. Let me see my Discord because I don't know where it's gonna. Do I even have Discord on here? No, it's not running. Okay, let's see if I have Discord on here. On this, I'm having to, unfortunately, I'm on two machines that are a decade old. So one I use for research, the other use for instruction. I have different applications on both. So let's see if I can launch Discord. If I can, I want to show everyone where they ought to be, because I'm going to deliver all course content moving forward through our Discord server. Canvas will be very minimal. I got burned with all the time I invested into Moodle. I'm not going to now invest any time developing Canvas.
Next semester it'll be something else.
Okay, so just wait for this to launch. And again, if you haven't joined the Discord, I created an announcement channel there. In the announcement channel, you can read you could read about the contents of the server. I created a videos channel that links to where our videos are posted, and I'll post lecture 4, I guess lecture 3. You know, I get what is it, lecture 3 and lecture 4? Yeah. I'll post both of those sometime this evening or sometime tomorrow, depending on when the processing is done on by Zoom into the playlist. I try to make it, so I took a survey several semesters ago from students to find out what's the most available route for them, what's the least frictionful, what's the frictionless approach, and it seems creating playlists through YouTube has been like the best. So that's how I did it. One playlist, you don't have to look around for videos. I'll just play one after the other for you to get access to. Oh, excellent. Yep, and it works on everything. Okay, let me see here. Somewhere on here, there it is. Okay, so here, CSAPP, right? Computer Systems, a Programmer's Perspective is the channel. There is an announcement section here that you can go through that kind of gives you insight on what are the channels, what are the roles. All students should have the CSCI2467 role because it allows me to go ahead and blast all of you whenever I add content to it. And then I also highlight the CTF Club server here. Feel free to go ahead and talk and use this space to communicate with your other classmates or to ask questions or just to interface however, right? So when you start working on the lab, if you're having any issues, blast in general talk. Here at the videos is going to be the updated list of what videos are available. You click on this link, it'll bring you right to the YouTube playlist. And resources, I'll build this out. In fact, I encourage you, if you have resources you want to add that you find valuable, throw them in here, right? But the current set of resources, I have all of the lecture material inside of Google Docs. If you had forgotten, last class I said I was going to make all my slides, which are they're Google slides. I would share a public link that not only gives you view access, but edit access as well. So it allows the entire class to come together and improve the slides for yourselves, right? So that if you have additional insights that you want to add, or if you find some of the slides too verbose, you can go ahead and edit them to be more summarized if you want. Like this is an interesting experiment that I'm doing. I've never given authoring access to the lecture material, but I'll see why not. Because I already have private copies of all of this as well. But you can click on this, and so I haven't posted this new slide deck because the slides we had today I just made earlier today, but I'll put those in when I go to publish the videos as well. And then the legacy, that 2467, where you can kind of see the older version of this class, that's also on here. Excellent. Okay. Is there any other questions? because now I'm actually out of time. Well, everyone, have a great week. I will see. Yeah.
So will the homework be posted on Discord?
Yeah, so I'll publish, I can go ahead and put the downloadable, and I can pin it too. So I can upload PDFs into the Discord as well. So that's likely what I will do. And then I'll also, yes. So go to the Discord to find everything.
And you said that.
But in the interim, you can still get the document, because the document's going to remain the same from this hyperlink. So if you click on that hyperlink, here, I'm going to click on it now. If you click on this hyperlink in the resources section, it brings you to 2467. This is the official page that this class is modeled after. If you go to the assignments, you can actually read all the assignments you'll have. So all your homeworks are publicly available. It just doesn't have the right submission. It doesn't just have the right submission dates on it. Does that answer your question?
Yeah, and you said that we won't have class this Thursday or next Thursday?
This Thursday. No class. So, but I want you to use that as a lab. We won't have a lecture. Treat it as a lab hour.
So we won't have class this whole week.
Of course, yes. I encourage you to do so. And I encourage y'all to also be on Discord so online people can be a part of that as well. Excellent. Any other questions? Online, in person? Excellent. I will see you all next Tuesday then.